Low Earth orbit is crowded, more than 8,000 active satellites. Half of all close approaches now involve a single name: Starlink. Tonight, one of those close approaches goes wrong. 2 satellites, 1 failed maneuver, and in less than a second, a collision that turns precision-engineered spacecraft into a high-velocity minefield. For the next 4 minutes, the global internet hangs by a thread. Starlink isn't just a sci-fi headline, it's infrastructure. Thousands of small satellites in low Earth orbit, arranged in shells and planes. Each one is a moving node in a mesh network, beaming broadband to ground terminals on every continent, remote towns with no fiber, ships crossing the Atlantic, aircraft flying over oceans, emergency responders after hurricanes and wildfires. For many of them, Starlink isn't a backup, it's the only link. And because these satellites fly just a few hundred kilometers above Earth, latency is low. That makes them attractive not just for rural users, but for financial networks, data backhaul, and critical communications. We've quietly tied more and more of our digital nervous system to machines rushing around the planet every 90 minutes. Our scenario begins with a routine problem: a single satellite in trouble. A Starlink unit in a 550-kilometer shell has lost part of its attitude control. It can still talk to the network. It can still fire its ion thrusters. But its ability to point and maneuver precisely is degraded. Normally, this isn't catastrophic. Constellation operators track conjunctions, close passes, and command tiny course changes days in advance. Tonight, a second satellite in a crossing plane needs to pass just a few hundred meters away. Under normal conditions, both vehicles adjust, but our damaged satellite responds late and imprecisely. By the time the ground realizes the automated avoidance has failed, there are seconds left. And in those final seconds before impact, we find out how fast one miscalculation in orbit can turn into a global communications nightmare on the ground. Relative speed, about 14 kilometers per second. That's 31,000 miles per hour combined. At that velocity, there is no such thing as a small crash. Even a glancing blow would vaporize solar panels and antenna arrays, throwing out shrapnel at several kilometers per second. In our case, it's nearly head-on. 2 1/4-ton satellites become tens of thousands of fragments, most smaller than a fist, each one a bullet in orbit. The chain reaction has begun. This is Kessler syndrome in microcosm, a density of objects so high that one collision breeds more, which in turn raises the odds of further impacts. The initial debris cloud spreads along the original orbits, forming an expanding shell of fragments. Some pieces remain in roughly the same altitude. Others are thrown slightly higher or lower, crossing adjacent Starlink planes within minutes. Every surviving satellite in those planes is now flying through an area of elevated risk. Most survive. A few do not. Secondary hits don't need to be as energetic. A small fragment shredding a solar array or piercing a propellant line can kill a satellite just as effectively. Each additional loss adds new fragments. The constellation begins to erode from the inside. And when mission control finally sees what this erosion is doing to the network, they discover the real problem isn't just losing satellites. It's what happens in the 4 minutes when the world suddenly can't reach the systems it thought were always online. The mesh depends on overlapping coverage. When you remove enough nodes in one region, coverage doesn't fail gracefully. It snaps. Beams that once had 5 or 6 satellites in view now have 1 or none. About 15 minutes after the initial impact, the debris ring has completed a fraction of an orbit. In our simulation, the worst-hit region is a band over the North Atlantic and parts of Europe and North America, exactly where aviation, maritime traffic, and data corridors are densest. First, users see what looks like congestion, slowing pages, buffering video calls, GPS corrections arriving late. Then, as more satellites fail or are forced into safe mode, entire beams drop out. Aircraft cabins lose in-flight connectivity. Remote oil rigs see their links freeze. Emergency services in rural areas lose backup communications. For roughly 4 minutes, large segments of the Starlink-dependent internet simply vanish. To the global network, it feels like a sudden, localized amputation. This isn't just about watching videos on a ship. Starlink and similar constellations are increasingly wired into backhaul for cellular networks in remote regions, telemetry links for infrastructure, redundant pathways for financial data, rapid deploy communications in disaster zones. When the constellation stumbles, these systems fall back to older, slower, or less reliable paths, if any exist. Some recover, others go blind. So the real question isn't, what if Starlink goes down for 4 minutes? It's, which parts of our world did we quietly wire to this network, without ever planning for the moment it fails? The blackout doesn't last forever. Earth still has fiber optic cables crossing oceans. Geostationary satellites still provide coverage, albeit with higher latency. Other constellations in different shells may remain intact, but the damaged Starlink planes will take months and hundreds of new satellites to fully rebuild. Debris gradually decays, but not quickly. Some fragments will haunt nearby orbits for years, forcing constant avoidance maneuvers and raising costs for every operator. Insurance markets react. Launch providers adjust. Regulators ask the question they avoided as the skies filled. How close did we just come to making parts of low Earth orbit effectively unusable? Our scenario is fictional, but the ingredients are real. We already have crowded orbital shells. Increasing reliance on LEO internet, near-miss conjunctions numbered in the tens of thousands each year. Mitigations exist: better tracking, autonomous collision avoidance, hard rules for deorbiting dead satellites, and eventually active debris removal. The question isn't whether a collision will ever happen. We've already had several smaller ones. The question is how many we allow. Before a single bad day in low Earth orbit becomes a bad year for the infrastructure underneath, because when we turn the sky into our network backbone, a chain reaction up there can mean silence down here. I am the cartographer, and this is the Atlas.